The next two homework assignments are I'll finish up the previous ones for Friday, but the next ones are posted. We have the documents for calculator and microwave up. These are, for these assignments, either calculator or microwave, same story as rhyming dictionary and physics engine. Choose one of the two to work to complete. And you're going to write the software, the logic software for a calculator or a microwave. And again, we'll provide the GUIs, so you can be able to play with these. The microwave GUI is not in a great state right now, but it will be updated to look prettier in not too long. But building the functionality for these, and as I mentioned last time, no control flow allowed on these ones. So no if statements, no conditional code, no loops. Nothing that's going to make your code run conditionally. You can't say some logic here. If this is true, this code runs. If it's false, this code doesn't run, which includes loops. Loops, if, switch, case, throw, try, throw, catch, any of that stuff. No conditionally running code. So we want to talk about how to be able to do that. How do we get different behavior out of our programming based on the current state of that program? That's what we want to build up to. So all next week, we'll talk about that explicitly with the state pattern. Today, we got to get some more background, polymorphism. So let's get into it. Any questions on really anything before we get going? Let's do this thing. Polymorphism. So last time we introduced inheritance. Let's talk about one of the maybe the biggest reason why we're using inheritance. Of course, we saw that we factored out common functionality. It reduces the times we have to duplicate code and duplicate logic throughout our program. Just take the shared logic, the shared functionality, put it in one class, and then extend that class and all the other ones that you create that want to have that functionality. So that's one big reason why we're using object-oriented programming in general. But let's see polymorphism, which would be a huge benefit, which is going to give us a lot more power, a lot more functionality without having really complex-looking code. We're going to be able to reuse code very effectively. To this end, we have one more battery, boombox, flashlight question. This will be the last one of these in this kind of series of three. In that electronics package, so you do have to have your functionality from Monday's lecture question, having the electronic class, boombox class, flashlight class that extend electronic, and also the battery class. So if you haven't finished that one from Monday, wrap that one up before you jump into this one. You won't be able to jump into this one yet. So the first one, just have all that functionality from Monday. For this lecture question, we want to expand that a little bit. Add this object named useElectronic, which has two methods. One, a useAll method that takes a list of electronics and calls the use method on every one of them. And a method named swapBattery, which takes two electronics and swaps out their batteries, as the name implies. So the functionality here isn't too complicated. I don't foresee anybody getting tripped up on implementing those two methods. If we treat the electronic class as a concrete class, just like any class that we've been working with, which you can do with this, just pretend it is, and just ask you to write a loop and call a method, and then do some swapping by references. Nothing too crazy here. Where we want to start thinking about polymorphism is in the testing. So when you write your test suite, we want to be able to test these methods, but these methods take inputs of type electronic. Electronic is an abstract class. We can't just create electronics and call these methods to test them. So how are we going to test these methods that use an abstract type that we can't really create? So this is where we take our boombox and flashlight, and since boombox and flashlight are both of type electronic, they extend the electronic class. They are electronics. We can create boomboxes and flashlights and use those as our inputs to test these methods. So in the testing is actually where we're going to start seeing the polymorphism and start seeing that, hey, I have a boombox, I have a flashlight, but I need electronics to be able to test this method. Well, those are electronics, so we're able to test that method through those concrete classes that extend the electronic class. So it's mostly the testing that we want to focus on here. How do we use these methods that work in abstract with abstract types that we can't actually create? So we saw the type hierarchy. I flashed this again briefly at the end of last lecture. Let's talk about this a little bit more. So this inheritance, these structures, inheritance type hierarchy here is showing the inheritance of different types. So at the very root of our tree, we have the any type. This is a class that is extended by absolutely everything in Scala. Everything is of type any. And from that, we have two main classes that extend any. Any val, which is going to be anything that's going to go on the stack. Anything that's going to be represented in stack memory. And then any ref extends it as well. And that's for anything that's going to go on the heap, anything that we're going to create objects stored in heap space, and then moved around by references. We have any reference. So anything that's represented as a reference extends this class, which of course includes everything that we create. Any class that we write is going to extend any ref. So we have our own little sub-inheritance tree, our type hierarchy here that we saw last class. So recall that we had dynamic object, which works with our physics engine. We have that from the physics engine homework, which has some functionality. We extended that with inanimate object, added some functionality to it, and then extended those in two subclasses. So we have two subclasses that extend inanimate object, which extends dynamic object, which actually extends, I don't have it on the slide, but that extends game object. And then game object, we don't explicitly extend anything, so it implicitly extends any ref, which extends any. So the implication of this is that health potion has 6 different types in its type hierarchy. There's 6 different types that a health potion is, that kind of fundamentally is. And we can store, where we start seeing polymorphism come into play, is we can store a health potion, an object of type health potion, in a variable of any of the types that it inherits. So we can create a health potion and store it in a variable of type health potion. Yeah, we expect that. We've seen that all semester. We would expect that to happen. But since health potion extends inanimate object, we can also store health potion in variables of type inanimate object. And this is where the magic starts happening. There are a lot of implications of this and a lot of cool things we can do with that fact that we're going to see throughout today's lecture and throughout the remainder of this week and next week. Inanimate object extends dynamic object, so a health potion by transitivity is a dynamic object. So we can store health potions in variables of type dynamic object and so on. Game object, any ref, any. We can store a health potion in any of these types because a health potion is all of these types. And this is where we get the word polymorphism from. Poly for many, morphism for form. So morph for form. So polymorphism, these objects have many forms. A health potion is 6 different things. It has many different forms that it can take for our polymorphism. So when we're storing these variables, these values, these objects in variables that are not directly the same type, we're using one of its other forms. That's when we're using polymorphism at that point. So recall that in the inanimate object class, we added this method named magnitude of momentum. We added that to the inanimate object class, and then our ball and health potion classes inherited that behavior, inherited that method, so they have that magnitude of momentum method. So when I have a health potion, and I'm storing in a variable of type health potion, I have all of the functionality for a health potion. I can call magnitude of momentum through that potion. If I store a health potion in a variable type inanimate object, potion 2 in this example, I can call magnitude of momentum. Magnitude of momentum is defined in the inanimate object class. However, once we get far enough up the inheritance tree, once we're storing a health potion in a variable of type dynamic object, that health potion still has a magnitude of momentum method. It's part of its definition, it's part of that object that's stored in the variable of type dynamic object. But since the dynamic object class knows nothing about magnitude of momentum, when I store this health potion in a variable of type dynamic object, I lose my access to that method. I can no longer access that method that was defined further down the type hierarchy. So from a dynamic object, I can't call any methods or access any state variables declared in either inanimate object or health potion. I can only use the variables and access the variables and access the methods that are defined, that are not defined, but declared in the dynamic object class or game object class or any ref class or any class. It has to be one of those. It has to be visible from that class. Great. So why are we even doing this then? I said polymorphism. You can store variable values in any type in its hierarchy, but you lose functionality as you store it in more generic variables. If you store a variable in any, for example, you can do almost nothing with that object. You can't do anything that's defined in any of your code. If you store in any or any ref, there's not much you can do with that stuff. So if all we're doing is losing functionality, why would we ever do this? So let's explore something that we can do, and one of the implications of this, being able to store values in variables further up the type hierarchy. So in our player class, we had these two methods, and we kind of had this, we didn't talk about it last time, but we kind of had this issue where every time we add a game object to our class, we have to go to the player class and add another one of these use methods. So we have these two methods. They really do the same thing. They just call use on its input parameter. But we have to have two different methods because we have one that takes a ball, use ball, one that takes a health potion, named use health potion. So if we want to add a new object to our game, it's adding to this player class, potentially breaking things, and just always revisiting this every single time we add a new object type to our game, a new inanimate object to our game. So let's change this a little bit. Let's refactor our code and start leveraging this polymorphism idea. So now, instead of having two methods, one for ball and one for health potion, let's write one method that takes an inanimate object. We have one method, use item now, takes an inanimate object as its input, and then calls that item's use method. Now I lose the access to any ball or health potion specific functionality, so I can't, for example, take this item and say, what's your volume? Because it only exists in the health potion class. It doesn't exist from inanimate object up the hierarchy tree. But we can access anything defined in inanimate object or any classes extended by inanimate object. Oh, I don't have extends dynamic object here. It should be extends dynamic object. So we have inanimate object defines two methods, object mass and use. And you might have been wondering last lecture, why are we defining these abstract methods? We have these methods with no definition. We have this use method that takes a player and returns unit with no definition. Why even bother having this here? Why don't we just delete this and just have ball and health potion both have a use method? We had to implement that, we had to write that code in those methods anyway. The only thing that changed when we added this to the abstract class was that we had to use the word override in front of our methods when we implemented them in the other classes. So why did we even bother doing that? And this is why. When we get a variable of type inanimate object, we have a guarantee that it has a use method that takes a player reference as input and returns unit. So it's not defined in the inanimate object class. Inanimate object doesn't say what that method does, but it does provide the guarantee that any class that extends it and is not abstract will have a definition for that method. If we try to extend this and we don't provide a definition, we're going to get errors. It's going to say, hey, you either have to be abstract or you better implement these methods. So we have a guarantee. If we have a variable of type inanimate object, we have a reference to something of type inanimate object, no matter how far down it extends, maybe it extends like 18 other classes, down the inheritance tree. A class that extends a class that extends a class, et cetera, that extends an animate object. It has to have object mass and use methods. It has to implement these methods at some point, or else you'd never be able to create an object of that type. It would never be able to be on the heap. We'd never have a reference to it. We couldn't get that far because all we would have is a class definition. It would have to be abstract, and we can't create objects of abstract types. So, but we can code to the abstract type. Take an inanimate object. I don't know where it was defined. I don't know what it does even, but I know I'm going to have a method named use that takes a player. I'm going to call it. Don't know what it's going to do, depending on whether this is in fact a health potion or a ball or any other type that we create that extends an inanimate object. This method call might have wildly different behavior, but I know it exists. I have that guarantee that it exists because it has to, because it's declared in the inanimate object class. So now when I want to call this method, I can have these variables, these values, these objects stored in variables of their own type, and they're very specific type. But once I call the use item method, I can call it on these types, and it's going to work just fine because those types are inanimate objects. So we have this implicit call, this implicit assignment. When we call use item, we're going to put a new frame on the stack. We're going to create a variable named item of type inanimate object and assign it equal to the value that is the reference that's stored in the variable ball. That assignment is just like the assignments we saw in the first few slides when we had some variable of type inanimate object equals some value of type ball, or some value of type health potion. It's the same thing, we're just doing it across a parameter being assigned to an argument through that method call. But the same thing is happening, so it's completely valid. Item inanimate object equals potion, completely valid. We have that potion, we're going to call that potion's use method on this player, and whatever functionality the potion has, healing the player in this case, that's going to happen when that use is called. When we call this same exact method with a ball as input, we're going to change the velocity of that ball and simulate throwing that ball in the game. So this one method can have wildly different behavior based on the type the type of the value, the type of the reference that's given in its call. And there's a huge advantage of this if we have a very large software and we have a lot of testing concerns. We're going live with this game. We don't want any bugs out there, and we want to make some updates and add new items to the game. That scenario I've been saying for a while. With our old setup, if every time we would add a new type of inanimate object to our game, we would have to add a new method to our player class, which means we have to go into our player class and start modifying that code. Which means our QA team is going to be on us and say, hey, you changed the player class. You may have invalidated all your testing. You at the very least have to write more tests for the new method that you added, and you have to make sure you didn't break any functionality that was already tested. We don't really want to do that. Every time we make a change anywhere in our program, we don't want to have this rippling effect where we could have had some unintended consequences far away from the change that we actually made. But here, with this, we have one method, takes an inanimate object. We're going to write tests for this one method. And now when we add new types that extend an inanimate object, we don't have to revisit the player class. The player class is done. We've written it, we've tested it, it's done. We lock that away. Unless we want to add new functionality to the player, maybe we want to add magic points or any other functionality here, we change this class. But if we're changing something that doesn't change the player fundamentally, we don't want to have to edit that class. We're not editing this class just because we added some other, because we added bow and arrows to our game. We don't want to go into the player class and say, okay, player fundamentally changed because you're interacting with a new object. No, we just want to say, here's how you interact with any object. Test it, make sure it works, done. Done with that class. Any questions to this point? So it's making our game easier to expand. There's also another thing we can do. We did this with inanimate object. We said, inanimate objects, you're going to extend dynamic object, and now you work with our physics engine. But we'd also like that same functionality with our player. So we're going to have our players also extend dynamic object, pass forward that location and dimension, and assign that velocity to the inherited velocity variable, making sure that our variable names are different. And now physics can be applied to our players as well. Our players are dynamic objects. We can store our players, our balls, our health potions in variables of type dynamic object. They're all things that can move around in our game. So they're all dynamic objects. And we'll revisit this towards the closer to the end of the lecture. Nope, we'll revisit it right now. So there's more. After this, we'll revisit this. We'll take a little sidetrack and come back to this. I forgot this slide too. So now that all three of those types are dynamic objects, we can create objects of those types, players, health potions, balls, throw them all in a list of type dynamic object. They are all dynamic objects, so we can store them all in the same data structure. We can give that data structure to our game world, and then our physics engine updating the world, all that physics applies to all of those different types. So when you're writing, for those of you doing physics engine, when you're writing your code, you never knew about health potions or players. None of your code cares about health potions and players, and it shouldn't. But that code, that physics engine that you write for that homework, can apply to these new types that it never knew existed, that didn't even exist before you wrote your physics engine. But it can work with all those as long as these types extend dynamic object. So in your physics engine, you only care about dynamic objects and static objects. Well, that's pretty boring. Like, we just have two different types of objects that have no meaning and no context. That's silly. Why are we even doing this? Well, it's because we're going to extend those classes with the types that have game-specific functionality and game-specific features in those classes that extend dynamic object. And those objects now, basically for free, have physics applied to them with the physics engine. Just throw them in the game world. The game world only cares that they're dynamic objects, doesn't care what they actually are. And then it's going to treat them as dynamic objects and move them around in the world as it sees fit, or as the laws of physics apply. Any questions on that one? We'll take a little bit of a detour after this slide. Okay. Let's talk about overriding a little more. So we've seen some behavior, especially in the last few lecture questions, from the classes that we create. For example, we get some functionality inherited from any ref. These two classes, they're implicitly extended by any class that we write. And there are certain methods implemented in these classes that are going to give us some default functionality from a few certain methods. For example, we have a toString method. This is declared in the any class, so absolutely everything in Scala can be converted to a string. You can always print anything to the screen because any has a toString method. So and everything is extended in one way or another from any. So absolutely every object in Scala has a toString method. We can print anything to the screen. We don't know what it's going to look like when we print to the screen all the time, but we're going to have something. The default for toString is to print out the object's type and then a reference, some value, some hash code actually representing a reference to that object. So we have health potions that we created, we print them out, and we're going to get the fully qualified name of the type, including the entire package, the @ symbol, and then some number representing its reference. We also have a .equals method. Everything in Scala has a .equals method, which is called through equal. The equal method is going to call our .equals. So every method, or every class, has a dot equals, so every object has a dot equals method. By default, as we've seen in the last few lecture questions, this is going to compare the references. So when I say I have 2 health potions that I create here, and potion 3 is going to equal potion 1, so I have 2 health potions stored in 3 different variables. Potion 1 and potion 3, this assignment was by reference. Potion 1 and potion 3, the variables store the same reference to the same health potion. So when I say potion 1 equals potion 2, well, these have different references, different objects, not the same, false. Potion 1 equal potion 3, these do refer to the same object. They have the same reference, return true. And that's what we were doing in the last few lecture questions. We were comparing these references directly through that equal method, through that default behavior. If we don't want that default behavior, just like we did with when we controlled the entire inheritance tree, when we had an electronic class with a use method, and then we overrode that method in our flashlight and boombox, when we overrode that, we can do the same thing with our default behavior with toString and with equals on the next slide. Override that toString method and give it whatever functionality we want. How do we want these things to print out? For physics vector, in that physics engine, we want that to print out. We certainly don't want physics.physics vector at some random number. That doesn't help us all that much. But we can override that and print physics vectors out in the way that we would expect a vector to be printed, x, comma, y, comma, z in parentheses. That's the way we want to see this information. Yeah.
So, based off of that, wouldn't 2 physics vectors that are named differently, which have the same values, would that be considered equal to each other?
In the next slide, we'll talk about that. So right now, we're talking about the toString. So if you had the same values in 2 physics vectors and printed them both to the screen, they'll look identical. We will no longer be able to see that hash code through the toString method. So they'll look identical to us at this point with this toString. But when we compare, until we get to the next slide, when we compare them with equal, if they're referring to different objects, we'll still return false on that, even though they print the same thing. Which can get confusing if you don't know what's going on. You print them both, they look identical, you say equal, and it's returning false. Can drive you nuts. But because the equal by default is comparing the references. ToString, this is some Scala syntax. You can leave off the parentheses if there's no parameter list. I don't like to, I don't recommend it. The ToString method does do this though, and since we're overriding it, we gotta use the same syntax. So no parentheses on the ToString overrides, if you're wondering about that. In Health Potion, if we just want to display all the information, we can override that ToString and display it in any way we want. This is a method that returns a string just like any other method we've written. We wrote. So whatever you want to display, however you want those strings to be formatted, you have full flexibility here. Just override toString and do however you want them to be printed. And finally, that equals, the equals method is going to take as a parameter, of course by default just checks the references. Do these refer to the same object? We can override this and change its behavior by overriding this equals method that takes an object of type any. So we only have access to the methods and variables, which I don't think there are any variables, declared in the any class. So not much functionality. We have access to almost nothing specific to our class for sure. And then returns a Boolean. Are these 2 things the same or not? And here we can say, look, we don't want to compare these things by references anymore. We actually want to compare the values and some of the features of these things and decide what it means for 2 objects of this type to be equal to each other. For that, we're going to use some syntax here, a match case statement. We're going to take this object and say if it matches any of these cases, run specific code based on that. So this first case, and this does matching based on the actual type of the variable that we get. So this is saying if this object happens to be of type health potion, store it in a variable named HP and run this code. So I want to say if I'm being compared to another health potion, and the volumes are the same, the values of the volume variable are the same, then return true. Say these two potions are the same. So I'm just concerned with how much healing potion is in each potion. If it's the same amount, I'm going to call that the same. That's the behavior I can get with this. And then the case underscore, that's saying, that's a wild card, this is a catch-all. If it's anything else that wasn't caught in any of the other cases, so in this scenario, if it's not a health potion, just return false. We don't want to compare health potions to any other types. It has to be a health potion and the volume has to be the same. Otherwise, return false. Yep.
So is using a match case statement not considered flow control?
It is considered. Yeah, so this matching case is something that's banned on the current homeworks. Any other questions? So now when we run this code, we get significantly different behavior. So we have two health potions, potion 1 and potion 2. They're different potions, they're store references to different potions, but they do have the same volume. So they're going to be true now. When we compare potion 1 and potion 2, their volumes are the same, they're both health potions, return true. These are effectively equal according to our definition of equal that we just wrote. And then printing them to the screen, when print line implicitly calls toString, we're going to get that format that we had in that toString method that we overrode. We don't get that health potion at whatever anymore. We get whatever string that toString method returned when we called it, when println called that method. So we have significantly different behavior now, and we can have a lot of flexibility. If we want to use equal, how do we compare two things? We can override that functionality, get it in any way, comparisons in any way we want. Whatever we decide equality means for our types, we can define that behavior. We also lose some behavior. If we want to see if two potions are the same, I believe we can still access the hash code. I think that's the way you would do it. But if you do want to compare references and say, are these the same health potion? We can't do that with equal anymore because we overrode that functionality. That functionality is removed from the health potion class completely, and then we're overriding it with our new definition. So our new definition is the new behavior of equal now. Let's revisit jumper, and I recommend, even if you're doing the rhyming dictionary, at least get a feel for the jumper code. We'll be talking about it a fair amount, especially this week and next week. It'll come up a few times. Even if you're not doing that, take a look through the code that's provided, even if you're not really working on physics engine code. There's a lot of code provided there that you're not expected to understand while doing the physics engine homework. You only have to do the physics engine code for that. You don't have to understand what else is going on in the program. But there's a lot in that program that we are going to learn how it all works over these next few weeks. So I'll start referencing that and saying, hey, if you looked through that code, you saw this thing, and I'm going to explain, hey, this is what's actually going on there. This is how jumper works. By the end of the semester, you'll be able to understand all of the jumper code. You'll be able to know all of how that works. So let's make some connections here. Let's talk about this polymorphism, what we learned here, and how it's applied in jumper. But another thing I want to mention, jumper, the jumping physics itself in the jumper game uses the state pattern, and we'll talk about it next week. But if you want an example of the state pattern, take a look at how the jumping mechanics work in that jumper game. There's a fairly complex feature set for the jumps. For example, there's a double jump. There's if you hold the key down, the jump button down longer, you'll jump higher. If you give it a quick tap, it'll just be a small jump, like we would expect from a platformer. If you're moving and you jump, you'll jump higher than if you jump from a standstill. And something else. There's some other functionality, I believe. But fairly complex jumping behavior, and that's all accomplished through the state pattern. So we'll talk about it next week, but if you want to get a head start looking at that, I'm trying to see what's going on with that state pattern, what's going to be happening in these homeworks that were released. You can take a look at that. For now, let's focus on the physics side of things, the physics engine side of things, and say, how does the jumper game apply physics in collisions when there are not necessarily dynamic objects and static objects? I worded that weird. But anyway, let's see how this works. So we have the static object class, which our physics engine knows about. We have the dynamic object class, which our physics engine knows about. But that's all physics engine knows about. It doesn't know about players, platforms, and walls, which are all part of the jumper game. So to do this, I have this intermediate inheritance, this jumper object that extends static object. We don't have to worry about this too much. I just needed unique IDs for each one of my objects, regardless of its type, whether it's a player, a wall, or a platform. So I created this class just to get unique IDs. I needed that for updating the GUI. When the screen scrolls up, I need to track all those objects and be able to render them. I just needed unique IDs, so I have this jumper object class, which just tracks those IDs. Then I have the platform class, which is going to extend jumper object. So by transitivity again, platform extends jumper object, which extends static object. So the platform is a static object. But I get to add more functionality to the static object, more than what the physics engine cared about. I get to add more functionality to that that's game specific and actually get features in my game, but still leverage the physics engine. So in the physics engine, there's these methods, collide with dynamic object, there's collide with static object. There's a few of these methods that don't really do anything. If you look through the code, or especially if you're working on the physics engine homework, you have this method, collide with dynamic object, which is going to set a few variables. It'll set a Boolean collided with the dynamic object to true. It'll remember what dynamic object it collided with, and it'll remember the face. It'll just set those into state variables, but it has no actual functionality. The only reason we store those values in state variables is for testing purposes, so we can test to make sure that our collisions are working properly. When we actually have static objects in our game, we don't need that testing functionality. That doesn't help us at all in building our games. It just helps us test that code without having a specific implementation of a game to apply to our physics engine. We're just shortcutting the game and saying, let's make sure the physics is working, and then apply it to a game later. So now we're ready to apply it to a game. So we're going to override that testing functionality, get rid of that testing code, and replace collide with dynamic object with our actual functionality. In this case, we have a platform, and we want to say, if this is the dynamic object that's colliding with me, if it's colliding with the top of this platform, set its z velocity to 0, and set its position to the top of the platform, so effectively landing on the platform. So I'm going to check which face was collided with, and if this player is coming down and hitting the top of this platform, we don't want it to clip through the platform, so move them up a little bit, move the player up a little bit, and set its z velocity to 0 so it stops falling. It effectively landed on that platform. If it hits any other face, if it's hitting from the bottom of the platform and hits that bottom face, we want the player to move up through that platform. We don't want any actual collision to happen. If it's hitting on the sides, any of the sides also, we don't want a collision to happen, and for a specific use case here, and also for an internal collision. If we say jump up from the bottom, colliding with it already, and now we're still inside the platform, still colliding, which would be an internal collision, we don't want anything to happen there either, just keep moving through the platform. But in this one specific collision, hitting the top of the platform, land on the platform. So we can add this functionality without a lot of code here. Straightforward, simple code, without having to think about how that collision actually happened. Because that was physics engine's job. We built that in physics engine, we tested that in physics engine, we made sure it worked. Now physics engine, we're done with it. Unless we want to add more physics features to our code, we're done with that physics engine. You finish the homework, you got your physics engine, you have a nice 3D physics engine, and you can apply physics. You can apply physics using that to any game. Here for Jumper, we pretend it's a 2D physics engine, so we're ignoring one of the dimensions. So you can use that physics engine to build a 3D game, all the same. You just have your objects implement functionality that cares about all three dimensions, and you get a three-dimensional game of physics. So we're overriding those methods that do nothing in the homework assignment, but we're overriding that functionality with our game logic without affecting the physics engine, without having to retest anything in the physics engine. We do the same thing with walls, except we're concerned with different collisions. If we hit either the negative or positive x in that direction, we want to collide with that wall. Make sure we don't clip, so move the player so it's just so the player's just touching the wall, and zero out their z velocity. Don't let them keep plowing into that wall.